All right, today we're going to take a look at section 4.3. I really don't like the title of this section. I'm using what they used as their title, which is Rules of Logarithms. I would prefer to use the word properties instead of rules because rules sound like somebody's imposed it from outside of the actual inherent, things that are already occurring. Properties mean that these are naturally occurring items. So these are really properties of logarithms. They follow these sort of prescripted ideas. So there you go. I changed the word right there. It says properties now. All right, properties of logarithms. So the first one is an inverse property. We encountered a version of this the other day, and I told you we'd talk a little bit more about it later. Well, today is later. So the first one actually talks about the fact that if you have log base A, and A is the interior of the component with an exponent x, this is just equal to x. What we had encountered the other day is we had a version of this that said something like log base 10 of 10 is equal to 1. And we talked about how as long as these match, this is always true. All right? So this is sort of an extended version of this. The exponent x actually becomes the quantity that this is equal to. The other one is that a raised to the log base a of x is also equal to x. Now, again, these aren't canceling out, right? They're really not, but it kind of feels like it. And that makes sense, right? Multiplication and division are sort of inverse operations. Well, logs and exponentials are as well. So they invert one another. They undo the other operation, which is why we're ending up with the x left over. All right? So it doesn't matter what the a is. It could be e, it could be 10, it could be 4.738. Doesn't matter. Any value in the place there will work. All right, so we're going to do a couple of examples, pretty straightforward ideas. We talked about last time when we have log and there's no subscript written down, what is the understood subscript that's there?
10.
10, good job. So if you take a look at this one, what we see is we see this 10 and this 10 matching. So what would this quantity log or log base 10 of 10 to the y plus 1 equal? It won't equal 1 to the y plus 1. That's a good guess. You're close. Any other guesses? Just y plus 1. Yeah. It's just the exponent. Okay, so this just equals the exponent y plus 1. On part B, we see sort of the opposite operation happening. We have 7 raised to the log base 7 of 999. Again, this 7 and this 7 are the same. So they're inverse operations. So what would this quantity end up equaling? 999. Okay, so these problems aren't meant to confuse. They're meant to be a recognizable feature. You recognize that the bases match, and then those are inverse operations, leaving you with the other piece of the expression. Okay?
Why does it leave the exponent?
I can show you an example. Would you like to see? Okay, do you want to do A or B? Because they'll be very similar. A. Okay, so let's say we had log base, and we'll put the base 10 in because it's easier to see it, of 10 to the y plus 1, okay? And we say we wanted to solve this for what is it equal to, and so I'm just going to call it equal to x for the moment. Now, one of the things we did in our last section is we looked at how to rewrite these in exponential form, and we drew this scorpion tail, right? And so when we rewrite this, we start with the base 10, we go to the other side of my equation, which is now x, and it's equal to where we landed, which is 10 to the y plus 1. Now, when we talked in this other section, section 4.2 earlier, we said that once we had the bases the same, we could rather ignore them and sort of compare the exponents at that point. And what you'll notice then is that the exponent x is equal to the y plus 1. And the exponent x is actually what we made up to begin with as this whole quantity. So this whole quantity equals x, and now we just found out that x is equal to the y plus 1. So we're kind of shortcutting the system and not having to rewrite every single one of these to find this out because it does work all the time. It's a good question, Deja. Does that make sense? And we could do the same sort of thing with part B. We could set it equal to x or whatever and draw our arrows around, and we could compare the pieces, and they would all fall apart just the same way, and we would end up with 999. Okay. Okay, 3 properties on this screen. I'm just going to let you write them down, and then I'll talk through them. There's a product property, a quotient property, and a power property. On the second one?
On the first.
Oh, thank you. Yes, that's a typo. Tyler's correct. There's supposed to be an N here, M and then N. Appreciate that. Okay, the first two properties, and I mentioned that we would see this happen when we talked last time, but the first two properties are very symmetric, if you will, or similar to the exponential properties that we had. One of our exponential properties says that if we have a to the m and a to the n, so that it looks like multiplication, that we then would add exponents together, m plus n. And you see this sort of feel going on with this problem as well. And they're related because these are inverse operations. So there's a sense that this makes sense that the same kind of property would come up again. When you have multiplication inside of a log, you can separate it out into two separate logs of the individual components. Now notice what it doesn't say. It doesn't say if there's addition and subtraction inside here you can do anything, right? It's not what it says. It's only talking about multiplication. And we should sort of have the feel that if multiplication becomes addition, that division would become subtraction. And in fact, the equivalent exponential property had the same feature, right? A to the m over a to the n. That looks like division, and it became subtraction, right? So again, that same kind of a feel going on with that one. The last one is actually far more related to the last pieces where we had the inverses than it is to exponential properties, at least a direct application. If you take a look at this example and you consider the property we had on the previous screen where it said log base a of a to the x, like this, and we said that this is equal to x, notice what would happen if you applied property, I don't know, I called it number 4, I guess, to this. This property says I can take the exponent and I can move it to the front. It becomes a constant multiplier instead of an exponent on the inside of the log. So this x, if it comes to the front, would be x log base a of a. And we talked about last time that any time we had the bases the same as the interior of the log, this is equal to 1. And so this would actually equal the quantity 1, and I would be left with simply x. Okay, so this property number 4 is an extension of that idea of inverses that's going on. Okay, so products inside logs become individual logs that are added. Quotients inside logs become individual logs that are subtracted. And exponents inside logs become constant multipliers. And we're going to use all three. The reason there's no examples here is because all three of these get used simultaneously. When you use one, you usually use at least 2 of these properties, okay? So we're going to see some examples next of how to use these properties. There's 2 different things that we're going to see. We're going to see logs of a whole bunch of stuff all crammed in together where we expand it out. And we're going to see expanded forms where we condense it back in, okay? So let's see which one's first. First, we have the single logarithm. So these are the condensing back in. We have separate logs. Notice they have the same base. That's important. If they didn't, we couldn't do anything. And they're separated with an operation that's addition. So which of the properties on the previous slide, 2, 3, or 4, would we be using on this problem? The product, property number 2. Basically, we have something that looks like the right-hand side, and we're going to condense it to look like the left-hand side. So, based on what we've written down already, how would we do that? What would it become?
You would it be log base 3 x minus 1 times x?
Yes, it would. As far as I'm concerned, it's fine for you to leave it like that. If you're checking the back or if my math lab doesn't like it, it might want you to multiply the x minus 1 and the x together, actually multiply those out. So another version of this would be log base 3 of x squared minus x. Okay. It was addition, and it became a product on the inside of a log. Okay, part B is a really good example of what I mentioned earlier. There are two properties at play here. Can you tell what they are? What do you see? Tell me something you see, Andre. You look like you're just dying to tell me something. What do you see?
I see exponents and division.
Okay, so you see exponents, these coefficients becoming exponents. Does everybody see that? That's important. And then you also see the subtraction, which is going to become division. Very good. Those are the two properties. You might look at this and think, well, which one's first? Actually, the exponent one would be first, because if you think about order of operations, multiplication would happen before you actually do a subtraction, right? And these pieces are multiplied, whereas these pieces overall are subtracted. So it is the multiplication property that will happen first. So if we take a look at this, what we're going to do next is we're going to write down the natural log of 6 to the 1/3 minus the natural log of 2 to the 1/3. Now, there's another variation of this. I'll do it second so you can see another way to think about this particular problem, just because it has kind of a nice form. But in general, we would deal with the exponents first. After the exponents are dealt with, we would do the division that Andre mentioned. These two pieces are divided. Notice, we don't divide logs. The log, in this case natural log, is only written once. Okay? Don't rewrite it. It's not log divided by log. The logs are subtracted. It's the interiors of the logs that are divided. So this is what it ends up looking like. One natural log written down with the division of the other two pieces. Now, I mean, we have to simplify this. This isn't like the last one where we multiply out, a little bit of a polynomial. These are numbers that actually condense down. You might recognize or notice that this one happens to have the same exponent on the top and the bottom. So you could factor that exponent out, which is useful because you know what 6 divided by 2 is. It's 3. So there's two versions of the way that this is sort of finally written. You can write it as natural log of 3 to the 1/3. Or how else could you write this?
1/3 natural log of 3.
That's true, but we want to have products, not coefficient multipliers. You're correct. There's something else though too that's another option. You could use a cube root, good. So we could write it in radical form. And there's really not one of these that's preferable to the other, but if you're looking at different options or yours doesn't look like somebody else's, I want you to realize that that's okay. Either of these would be legitimate operations of dealing with this. Now, because of that 1/3 coefficient being the same on each problem, there is one other way we could have done this problem. What we could have done is we could have factored the 1/3 out in front and dealt with it like this. Again, this only works because they're both 1/3. If they weren't both 1/3, we couldn't do that anyway. But then again, if they both weren't 1/3, we might not be able to simplify this piece either, right? So if we do it in this order, then we'd have the 1/3 in front. We'd have the natural log. It would be 6 divided by 2 here. So we'd have, there's that 1/3 that you were talking about in front, Tyler. 1/3 natural log of 3. And then we would move the 1/3 in, so say the natural log of 3 to the 1/3, or cube root. Okay? So there's a couple of different ways you could process through that. And that's often the case on these, is that the order matters, but there's more than one order that will work, depending on the values you're given. Okay. Now, the next one is not going to have coefficients the same, which means that second option of factoring out the 1/3 becomes irrelevant, all right? So let's take a look at the third option here. This is messy. There's 4 pieces. Some of them have coefficients, some don't. Yeah, it's a good one. Okay. I mentioned on the first, or on the last problem, that the first thing we would want to do is to deal with the exponents, right? And that's true still. I mean, we still deal with the exponents first. So take just a second and write down what you think this should look like if you deal with the exponents only. Okay, so no combining logs, just getting rid of coefficients and making them exponents. Just do that piece first. So your first two pieces shouldn't change because they don't have coefficients, right? Yeah. The next two do, though. So we would have log of y to the 1/2, or you could write it as square root of y if you want, minus log of z cubed. Is that okay for everybody? Those pieces all right? Okay. Here's a cool fact. We had two properties over here, one that was products and one that was quotients. And as we get more and more pieces, you might start to wonder, how do I decide sometimes if it's a quotient or a product? And what happens if I factor a negative out? How does that deal with everything? The easiest way to think about it is if there's a subtraction, that piece will go in the denominator. And if it's addition, the piece will go in the numerator. Okay? Has to be all written out so that each of the signs are in front of the individual pieces, but we actually have that in our case on this one already. So everything that's a positive, which is the first one, it's understood to be positive. The second one and the third one will all be pieces that are in the numerator. Okay, and so we write log one time, and then I'll have a 2 in the numerator, I'll have an x in the numerator, and I'll have a y to the 1/2 or square root of y in the numerator. I'll write minus square root of y at this point. And then, because the last one has subtraction, its interior will go in the denominator, namely, z cubed. Addition in the numerator, subtraction in the denominator. Some resources will use the word condense here. So if you see the word condense, this is what it means. It means that you've got a single log. Your book seems to be using the phrase single logarithm, so it should be consistent and say that in my math lab. And this is where you would stop on your problem. Now, if, for instance, the numerator and the denominator had a way to simplify, we would do that, okay? So if there was an x in the numerator and x in the denominator, we could combine like terms, those kinds of things, we would. This one doesn't have that property. So we're done. Okay, we're going to shift gears. We're going to go the opposite direction. We're going to start with something that's all, formed like this, and we're going to expand it out. So they're going to phrase that as writing it as a sum or difference of multiples of logarithms. So you don't have exponents left, and you won't have quotients and products left. Okay, so on the first one, what do you notice is happening inside the log? Division. And division becomes subtraction. And so when we do that and we expand it, we get multiple logs. We get the natural log of, we have a plus b, and then there's the subtraction that shows up, and we have the natural log of a. Don't get overzealous and try to do anything with the a plus b. You don't have any properties that allow you to simplify a sum or a difference inside of a log. They just have to stay put. Okay? Leave them. And that's it. That's all you can do on part A. All right, on part B, you probably noticed first the division. So let's deal with the division first. Okay, deal with the division first. So if I rewrite this just dealing with the division, what will it become? Somebody help me out. Subtraction. Okay, so log what? What will I say? Uh-huh. Close. Good. Minus the log of 4. Right. Don't forget the repeated word or phrase or operation log. Okay, so we've dealt with the fact that there was division and we've separated into subtraction. Then we deal with the fact that I've got exponents that I need to pull down. So I can take this exponent and I can move it to the front, and I would have negative x log 3 minus log 4. Now, as you're looking at that, as your final answer, you might say, well, now wait a minute. The sign at the beginning is negative, right? And you just told me on the last slide that a negative goes in the denominator, right? And I did. But think about it. If you were to take this original expression, it has a negative exponent. Couldn't you move it to the denominator and make it 3 to the x? You could. So that's not an inconsistency at all. It's just a different way of expressing it. So this is correct. It would be equivalent to having log of 3 to the x over, 1 over 3 to the x times 4. That's okay too. It's just a different version of writing it. Okay, so we have this for our final answer. Next one. This one has something interesting happen as we finish it out. I'd like for you to notice that there's division, of course, but there's also multiplication in the denominator, right? So there's actually 3 pieces inside of this being multiplied and divided, so we will have 3 separate logs. All right, so as I write this down, I have, these are log base 2. Log base 2 of the numerator, which is 5. And then everything else is in the denominator, so I'm going to have 2 logs, but they're both going to be subtracted. So minus 2, log base 2 minus a log base 2. There are 2 things in the denominator, so 2 subtractions. What's the middle one going to say? Log base 2 of 2. And what's the last one going to say? Y.
So why wouldn't you keep the 2y together?
You could, but then you're going to see a product, and you're going to have to separate it out as well, because we're trying to separate all the multiplications out. So if you didn't recognize this right off the bat, and you were to say, write it like this, Sydney, what you'll notice is there's a negative in front of that. So yes, it will separate it out as addition, but the negative in front of the log base 2, 2y will apply to both pieces. Yep, Andre.
Why isn't the sign in between log 2 of 2 and log 2 of pi a plus sign since it's being multiplied?
Okay, so think about what happens right here. If I were to simplify this version of it like Sydney had asked, I would have log base 2 of 5, and then I would have minus log base 2 of 2 plus log base 2 of y. And what would happen to that negative? It'll get distributed. That's why for me, I think it's easier to just say if it's in the denominator, it's going to be subtraction. I don't have to worry about the distribution. I don't have to worry about the 2 pieces happening along the way. I just know numerator's addition, denominator's subtraction, and it kind of shortcuts having to do those pieces one at a time.
I don't think we're done with this problem.
Or not. Do you know what's still missing?
I think I do.
What do you think's missing, Tyler?
I think log base 2 of 2 is 1.
You're right. This expression right here is equal to 1.
Something was up.
Did anybody else see it? It's okay if you didn't, but a few of you did. That's good. Yeah, log base 2 of 2 is 1. We don't simplify log base 2 of 5, but log base 2 of 2 is 1. So there's a lot of ways we could write this. Let's see, we have log base 2 of 5. I kind of like writing the log base 2 of y next, not because you have to, but then writing the 1 at the end, your preference. Those are the 3 pieces. So if you can simplify a log base 2 of 2, you're expected to do so. It's an operation. Any questions on that one? Okay. I told you last time that I couldn't remember, and maybe you guys can tell me whether it actually showed up for those of you who've finished your My Math Lab homework at this point. But did you need to simplify the expressions that we used what I called, don't even know if I called it this, but they called a change of base formula. Did you have to do that in any of the homeworks? Did you?
Decimals.
With the decimals? Okay. All right, so this is sort of one of those unfortunate things where the textbook doesn't present the formula in the right order. So here's where it actually shows up. I gave you this formula last time, but here's where I'm officially giving it to you. This is called the change of base formula. If you have the log base a of m, this is equal to log of m divided by log of a. And notice there are logs written in the numerator and the denominator of that. That's different than the properties we've been working with, right? Where it's just dividing the m and the a, for instance. Now, we've done an example of this because we did it last time, but we will do another one. How can I rewrite log base 3 of 4.78, because I'm going to tell you, I would expect you to rewrite it before you use your calculator to do it. So what would the rewritten step look like using this formula?
Log 4.78 divided by log 3.
That's correct. Good job. Can everybody see where the pieces came from? Because you'll need to be able to see them too. Okay, grab a calculator if you have it. Let's figure out what a decimal approximation for this will be. Let's go with 4 decimal places because I think your book actually has you use 4 decimal places on a couple of problems. So just for consistency, we'll do that. Andre's got a calculator. Sydney's got a calculator. What'd you get, Sydney? I think yours is done.
1.424?
Yeah, that's what I got.
Okay, good. Is there a 0 after that?
Yes.
Okay, then we'll write the 0. If it says 4 decimal places, we would write the 0 down as well. Okay, is that okay? Yeah, just use the log in your calculator. All right, you might look at part B and say, okay, but part B doesn't sort of look like it's a change base formula. Well, as we solve for it, it will. We did problems like this last time. We looked at changing this into a log form, or a log form of the exponential. And we did that with the scorpion tail, right? We circled the base and drew our arrow around. Oops. Let me try that again. We drew our arrow around and we landed at the exponent. So when we rewrote this as a log, what came after log?
It would be 0.23.
Right, as the base, right, Jonathan? Yes, so my base is a decimal, which is totally fine. I can do that. What would be next? Just finish it out for me.
So it'd be log base 0.23 of 18.4 equals x.
Right. So if we follow our arrow around, it will rewrite the equation for us in this order. And then if you'll notice, the left-hand side looks an awful lot like the first problem on this particular slide, right? So how could I rewrite now the left-hand side so that it actually uses the change of base formula?
18.4.
You got it. Good job, Rebecca. Okay, so again, grab calculator. We'll do the division and we'll write it down with 4 decimal places again. Now, it's valuable to notice that I've put the squiggly lines that means approximates. I don't know that I'm going to take off if you don't, but the reality is you are approximating. It's lots of decimal places of approximation, but it's still just an approximation. Okay, so what does it give you for a 4 decimal place answer? Negative 1.98 what? 16? Okay, so is it okay to get an exponent that's negative? Sure, there's no problem with that. Now, if you got a base that was negative, you probably should go back and look for your mistake. No bases that are negative, right? But it's okay to have exponents that are negative, not a problem at all. Okay, I've got a couple more where we're going to be using these features, so let's take a look. C starts out looking kind of like the last problem. We're trying to solve for something that's in an exponent position. And I can't get the same base on both sides because I got 1.025, for goodness sake, and 3. There's no way to get like 2 to a power or 2 to a power. We don't have that possibility here. So we're going to rewrite it as a logarithm. I'm not going to draw anything. I'm not going to write anything. I'd like for you to rewrite the first one here, C, on this slide, as a logarithm, and then we'll make sure that you have it rewritten right. Okay. That's what my arrow looks like. I have log base 1.025 to the 3, or of 3. That looks funny. Hang on, let me try that again. Here we go. Equals 12t. Okay, you got a couple options here. We can either divide by the 12, which is fine, or we could rewrite the left-hand side with the change of base formula next. So which one would you like to do?
Let's rewrite it.
Rewrite it? Okay, let's rewrite it. So if we rewrite it, the left-hand side becomes log 3 divided by log 1.025. Rewriting is actually my favorite way of doing that part too. I like that option as sort of which step to do next. I actually like the idea of taking your calculator at this point and getting the decimal approximation on the left. Leave it long and ugly. I mean, don't chop off your decimal at 4 places just yet. Just leave it sitting in your calculator. So we'll write it down with 4 decimal places on my screen, but we're not going to clear out the screen of the calculator, okay? So somebody tell me, what do you get on the left-hand side when you do that division step? And we'll write it with 4 decimals for now as well. What's our approximation?
44.4955378.
Okay, I'll write it with 6 decimals. Can I go to 7.3 and stop for that for now? Are you good with that? Okay. What would our last step be? Divide by 12. And whatever your calculator still says.
It's 537. not
Oh,
73.
okay. I'll fix it. Better?
Yeah.
Awesome. Thank you so much. Okay. Whatever it says right now in the calculator, with probably more decimal places than these 6 even, just hit the division button and 12. And it will actually divide the full expression that's in there, the full number that it's keeping by 12. And then we will give that answer to 4 decimal places. So what would this be with 4 decimal places now?
30.7076.
7076. Okay? Not much different than the last one, just that extra step at the end of divide by 12. Okay, D looks different because it's not starting out as exponential turned to a log. It's starting out as a log, and we're going to do what? Turn it into an exponential. Because I need to solve for the base. Right now, it's that x is sort of, embedded inside of a log as the base, and I need to get it out of there in order to be able to work with it. So we're going to circle the x, draw our arrow around, and we're going to rewrite. So this is x to the 2.3 equals 12.33. Now, think with me for a minute. It looks a little bit funny to have the exponent 2.3, but let's just say it only had an exponent of 2. If this said x squared, how would you solve for x? You'd take the square root, right? But think with me. Oh no, don't oh no. A square root is the same thing as a power 1/2, right? That's the same thing. So when you square root 2 sides of an equation, you're really raising it to a power of 1/2. That's an equivalent way of doing it or thinking about it. I know we're not liking that very much at the moment. I can see it on your faces. But I need you to think about it that way in order to make sense of 2.3. Because 2.3 is not a whole number where I can take a root very easily. Some of your calculators will let you deal with it that way. I'll show you that in a second, and some of them just won't. So if you're dealing with it from an exponential standpoint, what you would do next, I'm going to move mine over just to give me some space, is you would use both sides and raise it to the power of 1 over 2.3. Now, I don't know what kind of calculators you guys all have, but I think most of you are using calculators that have parentheses in them, like you have the ability to put parentheses in them. So if I were entering this in the calculator, I would use whatever button you have that says and the exponent that comes next, and I would put the exponent in parentheses, 1 divided by 2.3. That's how I'd enter it in the calculator, okay? That's how it knows that it's raising it to the 1, but it's not just 1, it's 1 divided by 2.3. All right. What do we get for a decimal approximation on this? 4 decimals. Okay, does it have a second on that? No, you have to? Okay, good. And Sydney says, I've got 3. I've got other people nodding as well. Awesome. All right, so let me show you one other option, again, depending on your calculator of how you could do it. we mentioned square root, right? And a square root is the same thing as a root with an index of 2, agreed? That means the same thing. So depending on your version of your calculator and so forth, another possibility when we had the x to the 2.3 is you could take a root where the index is 2.3. And some of you have calculators that allow you to change indexes to be whatever you want, but some of your calculators may not. So if you do, you could put a 2.3 index on a radical for your 12.33. Okay, if you know how to do that, great. If you don't know if your calculator can do that, but you like that as an option better, ask somebody in the Success Center, ask me right after class, and we can figure out if your calculator does it. Those of you who have like TI 84s, I know where it is and I know how to do that, so I can show you that really quickly. Either way, of course, you're going to get the same answer, 2.9808.